Okay, let's get started. Hello, everybody. Can you hear me okay? Very good. I'm going to start desktop sharing. First, I'll start. Welcome. Let's see. We've got Albert, Daniel, Ming, Junie, Kang. Welcome. Yeah, I don't have the mics turned on for me, so you can use the chat window here. Can you see the desktop okay? Okay, very good. Tonight, before we start, are there any questions about the class? There was a question about when things were due. If you look at Canvas, the first homework assignment is due at the end of next week. Not this week, but next week. The reason I don't put anything due this week is because there may be some ads. So they don't really start becoming due until next week. And if you looked at it, homework chapter 1 and chapter 2 are both due at the same time, the end of next week, as well as we have test number 1 open from Friday through Sunday next week. And we have our first CC Confer question starting next Thursday. I'll answer it either next Tuesday or next Thursday. I'm not sure which. Okay, any other questions, general questions? They're essay answers, Kang. And I covered that on Tuesday. Did you review Tuesday's session? I have the session here. I was able to get it, and it's a YouTube-like. It's a lot better than the CC Confer. I mentioned that in an email. I think I sent an email to you guys yesterday. Okay. Are you a new ad? That's probably why you weren't on my register yesterday when I took it out, when I sent the email. But what I said was you need to review the Tuesday session, and this link will take you to a YouTube version of it. And probably tomorrow or the next day, I'll have tonight's session, and I'll put it after here. Is it pronounced Junie? Junie? How do you pronounce that? Junie. Okay, thank you. We were in the middle of discussing chapter 1, so I want to finish discussing Chapter 1. These PowerPoints are available. This particular PowerPoint is available for you. We left off at this slide. One thing, and I kind of have the picture from the last time, I think. Maybe I don't. No, I don't have that picture right off the bat. But what we talked about was in this computer environment, you have, let me go to the notes and type this. You have operating system code, and then you have application code, and then you have all the hardware. What we're trying to understand is, how does the operating system manage the hardware and the application code? And what are the words around it? And this first 2 weeks, guys, is probably the most we'll spend in hardware, and the rest of the time we'll spend it in the operating system software. But I want you to understand how the operating system gets control from hardware activities and from the application when they request some kind of service. Application code can't access the hardware directly. They can't. You don't want them to. You don't want a user writing C programs to be able to write directly or read directly into the hardware, any part of the hardware. And most of our discussion this evening is going to be how the operating system does that. What's the mechanism? Okay? And it's via interrupts. That's the only way that the operating system can get control, is via some sort of interrupt. I showed you the steps, they call the machine cycle, where it fetches an instruction, executes the instruction, checks for interrupts, does a DMA in or out if necessary, and gets ready for the next instruction. Repeats that cycle. All of that cycle of the CPU is synchronized. It's synchronized to a clock, a system clock. And I'll give you some illustrations of that in a bit. The way the application program gets a request to the operating system is via an exception or a track. And it's called an supervisor call typically, and it generates an interrupt. It's a software interrupt. It's not a hardware interrupt. It could also be a hardware interrupt. Okay? For example, if the software divides by 0, that's an exception. And it would generate the interrupt. Then the operating system would get control. The request for operating system service is a request for reading a file, writing a file, getting memory. Any of the requests that require hardware are going to be done through a request mechanism, and we'll talk more in depth on that. You need to understand that the operating system has two modes, typically, user mode and kernel mode. And what's important about these modes is the mode bit provided by hardware distinguishes what mode you're in. If you're in kernel mode, you're able to execute privileged instructions. Now, privileged instructions are instructions that do things like request I/O from a device, add memory to a process, set timers for the program, creates, if this was creating a new thread, a program is creating a new thread, it would be passing that to a privileged instruction to create the thread, structure, and all of that stuff. And we'll go through that in depth, and I think in Chapter 2. But I wanted you to be aware of it, that the hardware has basically several modes of operation. The Intel has four levels of security or protection. The operating system, the code, typically runs in either user mode or kernel mode. And I'll show you how we get there. And I'll illustrate on a very simple system tonight. If you have any questions, just go in the chat window and ask. In order to prevent the infinite loop, remember on Tuesday I gave you that infinite loop? You need some sort of timeout mechanism that will time out a program or a process. Programs, in my mind, are the same as processes. So you would set the interrupt timer, it's a special timer, after a specific period. And then the operating system would decrement the counter. And when the counter is 0, it will generate that interrupt. And usually this is set up before scheduling a process to regain control or terminate that exceeds that allowed time. So basically what we're saying is, here's the kernel, and remember the kernel is in protected mode, typically in the kernel, and this, or privileged mode, is another way to look at it. And then when it returns control up here, it's in user mode. So what happens is, let's follow this. User process is executing. It makes a system call. That system call generates an interrupt, and that interrupt forces the mode bit to 0. The hardware does this. The hardware sets it to 0. And then it continues the call, the system call, which is now in the kernel with privileged mode. Then on the return back to the user, the mode bit is set to 1, and then the return is executed. So basically the return is with mode bit 1, which means now we're executing whatever request we are. We're looking at the data, maybe it was read a file or open a file, and we request that data and we're looking at it in our program, but we can only use non-privileged instructions. Okay, so the architecture of the CPUs in today have privileged instructions, non-privileged instructions. And this is what I wanted you to understand, is how the interface, the operating system, really handles users' requests or other kinds of interrupts. It works the same way. Chapter 3, I'll take you through a complete design of this. So a process management is another activity that needs to go on. You've got to save. If you do switch a program from one process to another, you have to save the program counter, all the registers, all of that kind of thing. When we talk about multi-threaded processes in Chapter 4, we'll discuss this more. So these are some of the activities of process management. How do you synchronize processes? How do you communicate between processes? And finally, how do you handle deadlocks? That's Chapter 5, 6, 7, Chapter 7. Okay, memory management is Chapters 8 and 9. How do you handle memory? What are the different models? What are some of the algorithms for managing memory? We're going to learn those. Chapters 10, 11, and 12 are storage management. How all of that works. I showed you a previous slide that gave you the storage levels. This has to do with how things are loaded and access times and bandwidth, how much you can get through at one time through the pipe at one time, and who's really managing these different parts of the hardware, different parts of the hardware. It's mainly the operating system. The operating system doesn't really manage the hardware, the cache on the chip and that. Usually the hardware manages the caching, but not necessarily. In the older days, before a lot of caching was done, the operating system did manage the motherboard cache. Okay, and then finally the registers, and it says that it's managed by the compiler. Yeah, the compiler assigns registers during the compilation time to the program that's running, but I'll talk more about that in chapter 8, 9, and 10, I think. And then this just shows you how it goes from the file or the program from disk into main memory, into the cache, and into the hardware register. Underneath everything is an I/O subsystem. Okay, and it has general device drivers, typically. And then when your specific operating system is running on that hardware, there are specific drivers. Sometimes they come from the vendors. For the motherboard and things of that nature, they come from the vendors. For the disk drives, things of that nature. And this chapter 15, 16 has to do with protection and how do you protect things and the security. This is a fascinating chapter. So you have to worry about that. And let's face it, Microsoft did a terrible job on protection. The computing environments are blurring over time. In the 60s and 70s, they were mainframes. And in the 80s and 90s, they were PCs, LANs, and WANs. LANs, local area networks, wide area networks. And in the late 90s, we've got the internet. And now in 2000, we've got in 2010, we've got the cloud environment. So it's kind of blurring over time. I would agree with that statement. Client server. I remember I was one of the first in my company in '82 or '3 to install a Novell NetWare system that supported a program that we wrote for the users. It was a lot of fun. I really enjoyed that. We used DBase as our database product. And it wasn't one of the Ethernet. Ethernet wasn't invented just, well, I guess it was invented, but it wasn't implemented in the early '80s. Then they talk about the different kinds of protocol. Have you guys taken any of the network class? Any of you taken a network class? No? Okay. I think that, in terms of opportunities, networking is still pretty big, so you might want to look into that, and security on a network. I think those are two big items of potential raking in a lot of money. For the longest time, Apple was closed source. The original Mac in the '80s was closed, and then what happened was, I guess in the year 2000 or something, somewhere around that time frame, Apple started to use a version of Linux, and it was more from the open source kind of concept. Right here, this one. Sun Solaris was a great operating system. I had a number of Solaris or Sun boxes with Solaris running on it when I was a manager in the mid-1990s. As a matter of fact, I grabbed the Spark 10. I think we had a Spark 5. No, Spark 5, and the company went out of business, and I grabbed that Spark 5, brought it home. It doesn't work anymore. But that's chapter 1. Okay, so what I wanted to cover here is just a review. Multiprocessing term means what? Anybody? What's a few words to describe multiprocessing? It's when the operating system has to deal with what? In terms of hardware. More than one what? CPU. When you have to manage more than one CPU, you're multiprocessing. And in the core, it's exactly the case. Even in today's cores, you have 2 or 4 CPUs. Well, it still has to be managed. Multi-programming means exactly this environment that I'm showing you here in Windows, where I have Notepad running, I have the CC program running, I've got, or I guess this would be, and I've got Internet Explorer running here, and I've got all these programs running down here, Adobe, PowerPoint. So multi-programming means that at one time I'm executing more than one process. Multitasking, I don't like the book's definition of this. In my mind, multitasking is basically multi-threading. Because I'm coming from the mainframe perspective in the 1970s and 80s. And when I wrote multitasking programs, what I really wrote was programs that were able to split themselves and have more than one version of them running. In other words, more than one task of that one program. So today it would be called multi-threading. I talked about privileged versus non-privileged CPU modes. Privileged instructions are ones that operate on all memory, all I/O devices, and all users, etc. Privileged means exactly that. It's every instruction. Non-privileged instructions are ones that will add values to registers, branch to locations within its main memory domain, request service, etc. But non-privileged are always considered application programs. Those that are like Word, Notepad, everything you see here is an application. Okay, it happens to be on this graphical user interface that's maintained by the operating system. But the programs that are running under this operating system, this happens to be Windows 7, are these application programs. And they all run non-privileged mode. They can't execute start I/O on a device. That's an instruction, typically in a CPU, the start I/O. They can't execute an instruction that says start timer. They can't execute instructions that access memory that they don't already own. It's not allocated to them. They can't access that. So there's quite a few instructions really that programs, application programs, and application programmers can use. Now, that's when we're talking about the hardware. Now, when we're talking about the operating system mode, it's in user mode, meaning it runs non-privileged instructions, or it's in kernel mode, or operating system mode, another way to say it, which means it can execute any instruction. And Intel's protection modes are the following. Mode 0 is kernel mode. All instructions are allowed. 1 is multi-threads. Certain instructions not allowed. And all three of these are in kernel mode. And then 2 is I/O drivers. When Intel built the architecture, they envisioned that the operating system would use these 4 levels. It doesn't, because it's too complicated. The operating system uses 2 modes, kernel mode, user mode. So basically what happens is when the user is running, they're at level 3 in the Intel CPU. When an interrupt occurs, it goes to level 0 and stays there until it goes back to level 3 on the CPU. And these 2 aren't used by the operating system, not by any operating system I know. It's just too complicated. Okay. I'm trying to remember why I put this here. I was just, I guess, trying to show the address. Each of these addresses is 1 byte, and in hex it would be CC. So, and there's another byte here. There's another byte here. And in the case where you have 4 address lines, you could access 16 bytes. And let's see. There's a I talked about this on Tuesday, how memory accesses, how the hardware accesses memory. And we did a fetch. You remember that, guys? If not, you can review the session. In general, he didn't talk about the programming language levels. Machine code is the instruction level. Machine code. That's the instruction level. The next level up that people started to write was assembly level. And you could take an assembly level class here. It would be kind of fun to do if you are more interested in that. But it's basically, an assembly is, you have one symbolic instruction, symbolic meaning a human could understand it, and then you have the actual machine code. So one symbolic instruction equals one machine instruction. And finally, compilers came out. And the first compiler I remember is Fortran. Fortran was the very first compiler. They came out with others, but COBOL was for business compilers. And it's basically a high-level language, so you have one instruction, and then it generates many instructions. And these are typically procedural languages. And then finally, they came out in the 1980s and 90s and whatever, non-procedural languages like Focus. SQL is a non-procedural language. HTML is a non-procedural language. XML is not. These are all 4GL languages. To get anything working, you have to go back to being a procedural language. So that's why we have C, C++, Visual Basic, Perl. I mean, I could go on and on. Those languages are all procedural. Okay. I wanted to share with you a couple of diagrams. So let me go to the PowerPoint. Now these are on, yeah, this is what I talked about with you last time. And I took you through how this mechanism works. The program counter is the next instruction to fetch from memory. That's what is in here, it's an address. It goes into the address latch. A read or write event is occurring, and then the address lines are trying in all this memory, this huge amount of memory, to bring back whatever the data lines support. It's either 8 bits, or let's do bytes. 1 byte, 2 bytes, 4 bytes, or 8 bytes, depending on how big your data line is. And I showed you how during the fetch cycle that a byte is selected. Okay, and then the data latch gets latched because there's only one guy left and talking on the lines, which I showed you on Tuesday. And that's the data that's correct now. And all of this needs to be done through timing. Okay? So if that's the case, I have a processor that I built my operating system, my computer on, and it's a simple one. It's the RCA 1802 8-bit microprocessor. And the reason I would like you to take a look at that is, number one, it's for your understanding to see what it looks like, how it operates. It was a 40-pin chip, and it was CMOS, complementary metal oxide semiconductor, which meant it was the first one of all the different processors that allowed you to use a 9-volt battery to power the thing. Now it takes 5 volts typically, but you could use a 9-volt battery and it would power this chip to go. You had to watch out for static, but all of these little lines coming in, like here's the interrupt line. When this interrupt line goes high, the CPU goes through its cycle, just like I showed you, fetch, execute, check interrupts. It's going to do that. It'll check that at that point. And something happens. And what happens, I wanted to describe it with you to give you the idea of how it happens in these other systems. Because remember, I said you need to have an understanding of some of the hardware. And once again, if you don't worry too much, as long as you understand the concept that there is some hardware interrupt that will force a change on the CPU to take you to the operating system code. And I think I've got a diagram of that. Let me see if I do. Yeah, I do. Okay, here's how it would work. I have program A running, all right? An interrupt occurs. What happens is these two registers, the X register and the P, maybe I need to take you back. I apologize. I need to take you back to the diagram of the processor. So let's go back to the specification. Because you don't know what these registers are. And I'm going to show them to you. They're right here. Okay, so this bus, see the bus here? That's the data line. Those are the 8 bits, 1 byte coming in and going into these registers. The reason I picked this particular microprocessor back in the 70s is because of the mainframe. I was on the mainframe, and the mainframe had 16 general purpose registers. And this guy just fell right into that concept when I built it in '76. Here is the address latch, meaning it's going to go out this latch to memory. So this is the address side. This is the data coming in from memory side. You had 16 general purpose registers that were 16 bits, so 2 bytes. And the way you got the 2 bytes to load in was 2 to the 16 is 64K. So you could have 64K of memory attached to this processor. And it did what a lot of processors do today. It multiplexed it. In other words, it had 2 timings for memory. The first 8 bits and the second 8 bits. So this had a kind of a delay for memory in order to actually get 16 bits going out. And our current Intel architecture, 64 bits, uses something similar. These registers are all either 4-bit or 8-bit. Okay, and the P register is 4 bits. This P, that's the pointer to one of these 16-bit registers. So this P, if it's 000, is pointing to register 0, and that's the next instruction to fetch. If the P were 1111, then this is the register, the F. This would be an F register. This is the one that has the address to go out on the address lines. Is that clear? Any questions on that? Is anybody confused? You say yes. Wow. Yes. Okay. You win. Just stay with me on this, and it might come clear. So I have a 4-bit, and it's going to tell me which one of these registers is going to be going out to the address lines, fetching the next instruction. Is that clear? Does that make sense to you, Shun? Good. Okay. All right. That's all at this point. The X register is the pointer to data. So the idea here is, and this is true in almost all processors, you usually have a data pointer and you have a program pointer, and more than one. So this is the same idea. There's 4 of them, and one of these could be pointing to the data. So I could be moving data in and out based on this register that's right here. If it's, let's say it's 001. Well, that would be this register, 001. And so that would be the address of the data to fetch. Okay? So T is a special temporary register, and it's 8 bits. It's 8 bits. And it has a purpose. If you think about it, if I'm executing, let me go back to this diagram. Let's see, where is it? Oh, I think I put it here. No. It's not in this one. It's in this one. Yeah, it's this one. Okay. I'm in a program. The program is executing, and an interrupt occurs. An external interrupt. I need to save the state of A and then load in where the operating system is so that I can handle that interrupt. So program A, an interrupt occurs while it's executing. The X and P, those 2 4-bit registers, get stored in T. And this is the key part right here. X is pointed to register 2, and P, the program pointer to the register, is 1. Interrupts are disabled, and then a fetch is occurring. So, going back to this diagram, a program is running happily. Let's say it's running from here. P is in like 6, register 6. And it's running along, and then all of a sudden an interrupt comes in through the interrupt line. Well, the CPU says, oh, I got to save the P, and it's 6. I have to save the X, let's say it's F. It's F. I save the F, and I save the 6 in this 8-bit T register. I turn off interrupts so I don't get re-hit, and then I change the P to 1, which is this register, and I change the X to 2, this register, and I do a fetch. Now I'm in the operating system handling that interrupt. You have to have that kind of mechanism occurring in your processor in order to get to the operating system. There's no other way to do it. Okay? So now what happens when you're now in the operating system? What does it do? Let's take a look at that. It starts whatever the operating system handler is in this P1 register. It starts that. And you do a save instruction to save the state of the machine. You save the registers, and now you do whatever the interrupt is supposed to do. You restore the registers, and you issue a return. And a return puts everything back the way it was. It takes the T, whatever was in T, the X number would go in X register, and the P number would go in the P register. So basically, remember, it was F, and this was 6, and it starts it up again. Starts the process on a fetch. And now we're back to where we were. And everything's hunky-dory. Okay, I'm going to show you again and again, so don't worry. This is just one example. I recommend you taking a look through the amount of the stuff I gave you. I gave you a lot of stuff on the 1802 on Canvas. I zipped it up. This stuff. CPU and this RCA 1802 information files. And I gave you an assembly language. This was the first PC, 8088, but that Intel processor was what IBM built their PC on in 1981. And then they went to 8086, which was a true 16-bit. This was not a true 16-bit processor. The 8086 was a true 16-bit processor. Then they went to the 286, the 386, the 486, and then they started with the Pentium 1, 2, and 3, and then they went to the cores and stuff. I don't know what the heck they've got today. I haven't looked at it recently. But you can't really get your hands on the internal architecture and stuff, but you can on these older ones. So that's why I'm using them. Let's take a look at some more of this. Specifications. Because I think you can see things using it. I just wanted to go to where you don't need to. This is all temperature and stuff like that. Here. This is a good thing. All processors go on a clock. There's some kind of a clock that times every activity. And in this one, you see that there's a fetch cycle and an execute cycle. And on the fetch cycle, there's the high byte. Remember I said it broke it up into 2 bytes? There's the high byte going out. There's the low byte going out. And then what gets read in is the high byte and then the low byte. So you can access 16 bits. And these 2 pulses are when they get triggered. These 2 pulses. TPA is when this guy should be available. This guy, the high byte, and then TPB, when the low byte is available, when the low byte is available. And then this byte is a memory write, so it's writing to memory, and it's complete right here. And then you have valid data. So everything is timed, so this is called synchronous. Memory is clocked to this. And in the case of this particular processor, it was 1 megahertz. So what that meant was 1 million pulses a second. And each cycle took, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So there were 16 cycles. So divide 16 into 1 million. You would get about, what, 100,000? So it could execute 100,000 instructions a second, this particular process. And some more waveforms and timing and stuff. We're going to skip over that. Just interesting stuff. But I wanted to go to the interrupt servicing. This is what when you look at a processor, and this is what operating system designers have to do. When they look at a processor, they have to understand how do the interrupts work in that processor. How does memory go with that processor? okay? And any other kinds of supported chips, because a lot of processors need the interrupt hardware, so you need to understand that. Well, this is this one that goes through about the X and the P, what happens, where they get stored, and that was to explain the this process. Okay, I'm not sure how much more hardware we want to look at. This was the thing I built in '76. I used this popular electronics article to build it, and what I like about this article is it shows you how to build it. You know, if you have any knowledge of diodes, things, you could build this. I did. And there's the parts list. This was an excellent article, but also it explains how things work in a more higher level than just looking at the specifications. Okay, so it has an introduction to programming and things. So if you're interested, you could go and take a look at that. So I supplied that. The other thing is the assembly, the 8088. Okay. Are these assembly instructions? Okay. I'm just going to demonstrate it real quick with you. I have a virtual machine, and I use VirtualBox, and I'm going to be showing you these operating systems. Right now I'm going to show you the XP because I've got something I wanted to show you with that. But I've got Ubuntu installed, and I've got Windows 10 installed, and I've got DOS installed. And we'll go through those when it becomes necessary. Right now we're just going to show the Windows XP. What I did is I went to a command line version, and I put in this program. So I'm going to show you the directory. And I have this test SO file that is a loadable module for Apache. All I did was move it, copy it from the Apache register area here, because I installed Apache and PHP and all those other guys. And I wanted to show you this program. This program is called Debug. Debug, and you can say the file name, and let's see, I want to make sure that this, okay, I think it'll be all right. I could do list, L for list, no, dump. And what you're looking at here is a hex dump of the actual code of the program in hexadecimal. Okay? What's nice about debug is you can unassemble it. Watch what I'm going to do. I'm going to use U for unassemble. And this is the first instruction. It starts at 100, register 100. And it's the first instruction. This is the symbolic name of the instruction. This is the actual instruction right here. 4D, or dog. It decrements this base pointer, BP, base pointer. And then it uses a pop to pop it on the DX register. Okay? So it's doing some stuff to get prepared. And you can see these are all machine instructions. Right here, they're all regular machine instructions. This is the mnemonic of what it's doing. And let's keep looking at it. And it's adding a bunch of stuff. And the important thing I wanted to show you is right here. This int21 is an interrupt. And this is going to call the operating system, and a 21 happens to be an open. Okay, so what it did was it prepared for that using these registers, and then it executed the interrupt. And right here, it would then go to the operating system. The operating system would handle it based on here, and then it would return back to this. And that's why it does a push on the stack pointer. Okay? So this area here in C programs would be an API, all of this stuff. And that's what the author was trying to tell us in chapter 1. Okay. So this mechanism allows the operating system to take control and service that request. And, oh, I wanted to show one more thing. I'm sorry. I thought you'd be interested in this. I want to show you the registers. See, these are the different registers in this as to what the address is. And these are the flags, the CPU flags that are set. So a non-zero is going to get triggered. So if the program divided by 0, the non-zero flag, we don't know if it's set or not, but I'm assuming it isn't. The IP is the instruction pointer, and once again we started at 100. I'll talk about this over here, the actual segment code. The actual segment code starts at these addresses. We'll get more into that when we talk about memory in chapter 8. Okay? But we probably won't go to this deep level. Okay, I've shown you, and that explains all of that in this chart. Okay, so that's probably as depth as we're going to get. Let's look at chapter 2 and start that, unless you have questions. I talked about that. Yeah, I just need to open it. Chapter 2. Okay, we're going to look now at the structures of the operating system, what kinds of things are in it. We're not going to finish tonight, but we're going pretty good. And I covered quite a bit of this already. So it has services. Okay? So, for example, you have the user interface. That's this graphical user interface. Or, I've been on all of the different types of interfaces. Or, command line. This is a command line interface, right? Where you enter commands, like directory. And you can run a program like I could run Notepad right now. And there's Notepad up and running. Okay, so command line is one interface. Graphical, this thing, Windows and everything, graphical user. And there's another one called menu driven. The System 34, I remember System 38 I was on in the 80s. It was menu driven. You would have a menu line and you would just go down through the menus to do stuff as a user. Amazing. You don't see that many menu-driven operating systems today. Program that handles program execution, I/O operations, file system operations. I like this diagram. You're going to see it again, so make sure you understand it. But there's the hardware. Here's the operating system. These are the system calls that the program would make. at the application level. Right, here's the application level. Here's the graphical user level and user services. The operating system also probably provides a language like a shell type concept. And Windows, the latest versions of Windows has PowerShell. And I'm starting to look at that language, and I'm going to learn that because my thinking is that's a good language to base things on in the future of Windows. And I'd recommend you kind of look at that as well. It's called PowerShell. It's more prevalent, I think, in the latest versions of Windows. Communications. You want to communicate to other computers over a network. What about if there's errors? How do you handle error detection? Errors. We're going to talk about that. Resource allocation. It has to, if a program wants to run, you got to manage it. You got to give that program memory. You've got to figure out the user access to it. There's accounting, huge accounting. This task manager in Windows has a huge accounting mechanism, and there's all kinds of logs going on about what's happening on your system. All right, your resource manager has information about what's happening currently, but most of this stuff is being logged in a file, so you can use it for accounting purposes. We talked a little about protection and security, but we're talking about access to the system and resources. And if somebody's trying to break in, the command line interface, which I showed you the command line interface. You got to have something like that, and the command interpreter directs the entry. Shells, you could have shells. On the user interface, I really don't like icons because they're hard to understand. When I look at an icon, I don't know what the heck they're trying to tell us. Like this icon here. I'll hold it up and repeat the next slide. Okay, now I know what that means. Okay, I do know this one, but quite a few of the icons are kind of, to me, weird. That's why I always like words, because then you could just look at it. Let's see. Many systems include both. Windows does. All the current systems include both. A GUI and a command line interface. That's showing us, looks like a Unix-based system at the terminal. And when we discuss that, I'll bring up Ubuntu and show you that. The Mac, I don't have a Mac, and I personally don't want one. I've been tainted since the 80s. System calls. Your programming language has to have some kind of application program interface. They don't do a direct system call. They usually use this like printf or openf, right? Those are APIs. And there's an example of a system call. Okay. You want to get the name, and you want to write the prompt to the screen, have the user accept the input, acquire the output file name, write the prompt to the screen. All of that stuff that whole sequence, you want to make sure you can do that easily through an API. You don't want to write the code. Like, you don't want to write this internal code here that you see, this function, this readf function. You just want to use read file command. But this is what it's doing internally. And you saw some of that because some of these things here were in those registers prior to the interrupt. They were in the registers. So the handle, the buffer, pointer to the buffer, all of those programming things that you need to, that you as a programmer don't really care about. If you were writing an interface, you would definitely have to understand this. So, a system call. I think a diagram. Yeah, this is a good diagram. So the user application wants to open a file. So they use an API open, and so far you're in user mode. Okay. So far you're in user mode. Let me go back to this. All of this is part of the user mode, user mode, user mode, user mode, user mode, and the interrupt instruction itself has to be a user mode instruction. But this interrupt is going to force the CPU to go into privileged mode, right? Go to the operating system that handles the 21 request. And now you're in kernel mode. So right in this interface, this read, or excuse me, this open file interface, that line is the int21. That line is the int21. Now you're in kernel mode, handling that, and it does this open call for you and handles the hardware. Is that clear? Does anybody have any questions on that? Okay. I'm going to keep going. And here's another example where you have your C library. Here's a printf, right? If we broke printf down, eventually we'll find an int. It probably wouldn't be 21, it'd probably be another number. It would be an int, and then the rest of the stuff would get handled, and then it would actually write to the device, whatever it is. It could be a file, or it could be a monitor or something. Where it gets a little more complicated is the parameter passing. So let's spend a little time here. 3 general methods used to pass parameters to the OS. The simplest is in registers. Okay, so let's go back to here. Oh, wrong one. Here. Move this code to register DX. Move 09 to the half register of A, and call the interrupt. So these moves here are storing the data in registers, as an example. Okay. Another mechanism is is stored in a block or a table in memory, and the address of the block is passed. So in more complex service requests, this would be a good mechanism to use. And it says Linux and Solaris uses. These slides are from an older version of the book, and they're going to keep mentioning Solaris, but you all know Sun is long gone. I'm really sorry because they made great hardware. I'll just tell you a quick story. When I was, this is 95, 96 time frame, I was in a startup company called Arbor Software. And I was in the IT department. I was a manager of the applications group. And I installed a number of Solaris boxes that ran our application software on it. Yeah. And I remember booting it up in 95, late 95, and it never came down until I brought it down in late 96. So it ran for a whole year without an issue. I mean, it was an amazing hardware. Try to do that with Windows. Windows needs to be rebooted periodically, but not Solaris. Linux is pretty good. And then parameters can get placed or pushed onto the stack by the program and popped off. You kind of saw that in our example here. You see a push and a pop, a move, and an interrupt. Then a move and an interrupt and a push. So it's getting the data back. So there were two interrupts here. Both hit the operating system. Block and staff do not limit the number or length of parameters. Yeah, if you do it by register, you only have so many registers in your CPU. So you probably wouldn't do a lot of if you had a lot of data. And it's telling you how it works, which I showed you. Well, I didn't show you via table, but it would load an address and then do a system call, and then the address is known. See, the address X is known where it is. You might see these again. Process control, the type of call. File management is a type of call. Device management, information, communications, and protection. Those are typically system calls. And there's many. Windows and Unix. Process control, create process. Unix is a fork. Exit process, exit in Unix. Wait. So you can kind of see file management, how it would work. Device management, information, communication, and protection. These are simple, by the way. These are simple calls. There's a ton of calls available. Okay. I think I asked on Tuesday, did anybody work on a DOS environment? I don't think I got any answers. Is anybody here tonight who had done things with DOS? I don't see it. In high school. Oh, good for you, gang. But never used it. Okay. Well, let's go to our virtual machine and let's bring up DOS. First of all, MS-DOS only addressed 512 bytes directly. And there's a famous quote from Bill Gates back in 88, I think it was 87, 80, somewhere around there, that said, why would any program need more than 512,000 bytes? And of course that's ridiculous. But let's look at memory. See, there's 513K of conventional main memory. The first processors could only address about not quite a meg. Looks like half a meg. And then what happens was they designed extended memory. That was the first thing. And the 8086 could access 64K. Let me think about that. Yeah, I think it was 64K. And no, it was 20. 2 to the 20. It wasn't 2 to the 16. It was 2 to the 20. I didn't show you that architecture, but it could access whatever 2 to the 20 is. Let's see, 64, 128. Yeah, about 1 meg. I guess 1 meg or 2 meg. And this extended memory allowed you to get more memory. And use it. And so it was called high memory at that point. High memory is available. And the idea was you can only run one program at a time. I don't have any programs on here. I just have the operating system stuff. All of these programs are the operating system programs. So command.com is the kernel. It's the command line processor, command.com. I don't have debug on here, so I can't show you what the command line looks like. They did have check disk. They allowed you to add a mouse com. They had QBasic, which was kind of cool. I guess we could do that, QBasic. I wrote a number of programs in QBasic. Now the mouse doesn't work here. You could capture it, but I don't think it'll work. No, it doesn't work. So let me get out of that. Okay, yeah, the mouse doesn't really work properly in DOS. So you would use like Alt-F for file. Oh, I got to hit this too. Alt-F to get the file, and then you use the arrow keys. Okay, and then you could write your program. And then you could run it and edit it and do stuff like that. Okay? I'm going to do exit to exit. Okay. But that's the only program you could run. You couldn't run 2 programs at one time. And that's the environment that this is talking about. You have the command interpreter in low memory. And the kernel, there really wasn't much kernel. It was this. I guess the kernel was, you see, sys config.sys sys.conf. This was really the kernel, sys.conf. And then the command got loaded, command.conf got loaded, and all commands that you type in a command line would go and interpret through this guy. So that was the command line interface. Okay. Then when you load a process or a program in memory like we did with QBasic, you would have a certain amount of free memory that you could run another, but you can't. You could only run one program at a time. Then they developed, what was this environment called? Do you remember? I started you off tonight with the different names of things. What was this environment called? This might be a hint. It wasn't called that, but something pretty close. Multi-programming. Excellent, Dale. Excellent. Multi-programming is when you run more than one program at a time on a machine. Okay? And that's what's happening here. And this is what makes operating systems so much fun, because you have to manage this environment now. The DOS environment was so easy to manage. You didn't have to worry. You know, a program run, and if it didn't have enough memory, it wouldn't run. If it had enough memory, it would run. This, what happens when process B finishes? You free up that memory. So now you've got free memory that you could run something else. And you have free memory here. Right? You have free memory here, free memory here. How are you going to manage that? We'll talk about it. That's managing this environment. There's many algorithms, memory management algorithms. We're going to show you those. And we're not going to do code, so don't worry. The most we're going to look at in terms of code is what I'm showing you tonight, and maybe on Tuesday. And the rest is going to be high-level stuff. So don't get concerned that you're going to get lost in the mire of the hardware. I just want to make sure that you can see the how it really works. So system programs, and the operating system comes with many programs. The file manipulation. Okay, so let's go back to this simple thing. When I do dir, I'm manipulating the file system. I can do dir and do a wide view. That's a file system command. Okay. Let's just set this aside over here. This one. Status information. I showed you that with mem. I showed you mem. It's status. File modification. Yeah. What do we do? Let me just do. I created a drive. I'll show you that when we do file stuff. So I'm going to go to the C drive, and I copied those files. So those are the same files that are on C drive, and I created this directory called testing. So let's remove directory testing and new directory, and it's gone. That's file manipulation. Programming language support. I showed you the QBasic program when you wrote print and hello and all of that. That was in that support. Program loading and execution. When I type it on the command line, I want it to run. You got to load it and execute it. We didn't do any communications. We did do application programs. If we had any here, we don't have any. So that's system programs. Any questions on those? How are you guys doing out there? I mean, is this interesting to you guys? Good. I like that. It's hard to tell, you know, when I just do a lot of talking, not a lot of querying about how you guys are doing. If you have any questions, just jump in, right? Don't be shy. Because we're moving at a pretty good pace. Okay, I talked about things, so I don't need to go over that. Oh, they did it more in depth. They did it more in depth. Yeah. For example, there are programs, there are internal commands. There are internal commands. Let me think a second. Like, for example, you didn't see dir up here. You didn't see dir. You didn't see that in this list, is what I'm saying. Because it's part of the command interpreter. It's inside that command file. And there's something else you could say type. And type will display. So I could say type, let's take a look at mouse ini. So this guy, mouse ini file. It looks like it's 28 bytes. And using ini files you can display. And there's what a typical ini file would look like. Looks just like that. Autoexec.bat is how the system in DOS, you could put up commands in autoexec.bat. It's a batch file, so it can use batch commands. And you could do stuff in it. Let's type out what it does. Okay, it looks like it turns echo off, so you don't see everything going on. And it runs the Microsoft CD device driver, and it puts it in the D drive, and it calls it banana. And it's got some codes. And what that does is it sets up the CD. That's what this guy does, the CD drive. And I put this echo in, and just to see if we could see the C drive. And I can't get the environment, this virtual box, to boot off of this C drive I created. It has to do with the virtual machine. But normally, you could, in a regular DOS environment, boot off of the C drive. Right now, it boots off the A drive. Okay, well, anyway, that's these text editors and stuff. It happens to be that there's an edit program here as well in DOS. And, of course, Windows has text editors, Notepad, WordPad, that they supply. To me, it's really important to understand the design of an operating system. And the goals vary. Every operating system really has different goals and specifications. So your user goals could be convenient to use, easy to learn, reliable, safe, and fast. Would you guys say that this DOS program is easy to use? If you were, never saw a computer system and you were asked to do stuff on this environment, yes, it takes time to get used to, especially this, because you have to know the commands. or you need some kind of help. And they didn't install help. Help isn't in here. There is a help command but it was never on this drive. So, reliable, safe, and fast. System goals. Easy to design, implement, maintain, as well as flexible, reliable. Yeah, I think commands, Boomer, I agree with you. Command line stuff is important to understand. Sometimes doing it on the command line is better than doing it in a graphical mode. Graphical mode usually takes longer, but it's sometimes easier to figure out. When you design something, you have to understand the policy, what will be done, and the mechanism, how to do it. In Chapter 14 and 15, we're going to look at this. Okay, this concept of policy versus mechanism. Once again, there's a simple structure, and I'm showing you it. And this is the logical look of it. You have your application layer, your resident system, that's the I/O system I showed you, and then you have the device drivers and the BIOS, the ROM drivers that are on BIOS. Usually your I/O subsystem is in ROM, and then what happens during the boot process, right, that ROM BIOS gets moved into RAM, because RAM is usually much faster than ROM. So typically in the older PCs with the older BIOS, they allowed you to kind of play with whether you wanted to load the PROM stuff into memory. It's called shadow RAM. That's the word that they used. You want shadow RAM to be there. And most, I don't think they even ask that question anymore. I haven't looked at my BIOS settings in a long time. Well, and two, I haven't bought a recent computer. Every computer I had, except my laptops, I made. Let's see, next one. And of course, this layered approach is what we have today. The operating system is divided into a number of layers, levels, each built on top of layers. Layer 0 is the hardware. The next layer, or the highest layer, and is the user interface. With modularity, layers are selected such that each uses functions or operates in only lower layer levels. So what you're saying is that the next highest level uses the next lowest level, etc., etc., etc. You don't want to have a layer skipping a layer and doing something else outside of one of the layers. I think that's what they're trying to tell us. Do you guys know what Microsoft Windows calls their layering approach? I mean, I'm probably going back into the 1980s when Windows was first being created. No clue. I'll give you the 3-letter acronym, and you tell me what its name is. But what are the words? Anybody? What does COM stand for? Component Object Model. And that's this model. Okay, it's the Component Object Model. You have all of these DLLs, Dynamic Link Libraries. We'll talk more about those, okay, over time, so you understand what they are. In Unix, they're SOs. They're shared objects. In Unix, they usually end in SO. And I showed you one in XP. I had XP running. Yeah, I had XP Pro running. And I showed you that we were looking at a shared object. It happened to be Apache. It had to be an object of Apache. But it would be SO, and on Unix or Linux, it would be an SO. Windows, when they create them, with Windows, they're DLLs. Let me show you one. When we do this, see this, when we say File, and we say either Save or Open, okay, I'm going to cancel that. I don't want to do that. What happens is, well, I'm going to try it. I'll do Save As. It opens up a dialog box. This dialog box, okay. This dialog box is in a DLL that's in your system. Okay, I'm going to cancel this. And it's pretty much true, I think, in all Windows. And I'm going to go to that on my machine here. I'm on my Windows 7 machine here where I've got all this stuff. So I'm going to go to C drive, Windows, System 32. And you see these are all those DLLs. Let me think a second. Let's see. It's COM-CTL, I think. There it is. There it is. That guy right here. COM Control 30L, COM Dialog 32 are the common dialogues. You can even see it in the description. It says Common Dialog DLL. That's where the save routines are. The file open routines, they're in that DLL. That's what we mean by layered. Component Object Model. And it brought a lot of problems. This architecture has brought a whole lot of problems to programmers. That's why Microsoft created .NET, was to get out of this DLL hell. They just created a different hell. No, it's not nice. I shouldn't have said. Let me take a look at my system. I'm running slow. I guess because, yeah, my CPU is just working like crazy here. And that's because I probably don't have a lot of free space. It doesn't look good. Rudy. Okay. Let's go back to the slide. I'm going to close some of these. I just am using too much memory. So no, it's not you. It's my machine. Let me close up some of these. I only put them out there for a short period of time. Anyway, this will get me a little bit faster response time. I'm just shutting down my virtual machines. And then I want to turn off the box. Okay, that will help us get response time. Okay, what I'm trying to illustrate is the different layers or levels of our environment that we're in Windows. That's what I'm trying to accomplish with you guys. Is that clear? Rudy, are you okay on that? If you don't follow all the illustrations, that's okay. I just tried to show examples. What I want you to understand is that there's a layered approach to these modern operating systems. You should understand this stuff here. Do you understand that there's a layered approach? Yeah, that's one thing you can do. Thank you. Steve, thank you, Steve. Okay. Did you get the book? The booklet might help. I'm trying to cover it at a high level now, and I'm giving you specific examples. The things I want you to know, I'll say, you're going to see it again. And that means it's going to be on the test. Yeah, Unix operating system was really designed because there was a small computer that they were trying to work on. The DEC developers, Ritchie, and I can't think of the other guy who was doing the C stuff, kind of wrote Unix to help them as programmers. So it was built for programmers. This diagram you need to know. Okay, so you're going to see this again. And what it's representing is a layered approach, where you have layer 0 hardware, layer 1 the operating system, layer 2 maybe system services and stuff, and layer 3 the user interface, or layer N in this case. How are you doing on this, Rudy? Does that make sense, what I just said? Good. Okay. Thank you, Boomer. There was a terminology used for a while, the microkernel. And where this is, the idea is you can have a small kernel, a very small kernel. And that way it would be easier to port the operating system to new architectures if you had a small kernel. Therefore the word microkernel, small kernel. And I think this works fine from an operating system perspective if you are going to be porting it to other places. I mean, that makes sense. Okay. Can I get these notices? Let's look at Mac. Mac looks a little like BSD. The two major lines, if you will, of Linux or Unix was BSD and System 5 or 4, System 4. Those two lines were the first starting lines, and then they kind of grew into Linux. And what happens is people or companies add concepts to it. A lot of the open source stuff is pretty good. And they make them pretty well, and that's why I recommend sourceforge.org as a website for open source stuff. I get a lot of open source from there, and if you look at my machine, you'd see I have tons of applications on it. Some systems use modules where you're going to have, if there's a certain level of hardware, right, a certain hardware, it would add that module when it needed it. So they use this modular approach, and it's sort of like the DLL approach that Windows would use. I'm going to skip Solaris because it doesn't exist anymore. But it was a good operating system. I showed you a virtual machine. What a virtual machine does is it adds another layer to your host machine, the machine that your virtual machine resides on. And you have an environment to run a different machine. A little bit later, I will talk more about where the concept of virtual machines really originated from. And like most concepts that we're going to talk about, they originated from IBM on the mainframe. And they were one of the first to do virtual machines, was IBM. And I'll explain why a little later in our class. It's a great story. I have lots of stories. Okay. And there you go. I wasn't on IBM in '72. I was on IBM in '78. So let's see what else we want to say. This is really the primary reason that IBM created it, was you could have your production machine nice and running, and then if you had a new release to test, you could put that in your virtual machine, and have it completely tested outside of touching your production environment. So this was pretty critical. And you've got your non-virtual machine, which is just your operating system. And then inside a virtual machine, you have operating system number 1, operating system number 2, operating system number 3. And I think I showed you the virtual box from Oracle. That virtual box, I had 4 machines, 4 virtual machines on it. And it really slows it down. Yes, it is a fail-safe. For instance, if you wanted to test your operating system, like you're on Windows 8 or something, and you wanted to see what Windows 10 looks like, you could do that. You could install that. Once again, I have 4 virtual machines. I could install others. Of course, it all requires memory and stuff to run, which is why we got slugged down. But this version of Ubuntu I was playing with for a while, and now I have another laptop that Windows 8 failed on that I'm using for my Ubuntu, and I'm doing a lot of stuff on that, playing with it. So this was a good way for me to test it, to see if I liked it. So that is another example of a virtual machine use. You should try, I mean, it wouldn't hurt if you have the wherewithal to do that. Maybe next Tuesday or something, if somebody has a question, I could kind of illustrate how you would set up an operating system inside the virtual machine. And also, you got that request of mine, right, to use discussions, right, and to start discussions, because you're going to get points for those. And it looks like people have started. Looks good. Yeah, I haven't read this yet. So these look good. And then we've got responses. We've got 9 responses to that one. So this looks pretty good. I'm going to minimize this. Let's find the minimizer. On paravisualization, it's kind of a similar concept to a virtual machine, but I haven't seen this used. I really haven't seen this used much. In other words, you have to have the hardware. There's a hardware component that will allow this to occur. And it looks like it's mainly was done in Solaris 10. I think that was the last Solaris operating system. Was 10. Yeah, yeah, and it's not used today, so let's skip it. VMware is used a lot. It's a not a freebie though. The one I told you about, Oracle Virtual Box, you could look that up online. It's free to install, This one is not. The VMware is not. And it's a lot more robust, though. Okay? And some companies use that for their desktops. I mean, they do use a virtual machine. Virt Manager. Boomer, is that another vendor? Oh, Fedora. Okay, yeah. Well, yeah, I've used theirs, Vale. I started out with them, and there were issues with it, so it is for free, but I didn't find it as many features as the VirtualBox. But you're right, it's free. Okay, Java. Have you guys, anybody coded in Java? Yeah, okay. No. All right. That's okay. The Java, matter of fact, we're in Java. This environment that we're running, this CC-confer is using, let me see, Blackboard. It's using Blackboard. Blackboard is a company that allows collaboration, and because this is a class, CC-confer can use Blackboard's product for free. So De Anza, being a college, can use CC-confer for free, which is why I use it. It doesn't cost anybody anything. And they're using Java. All of this Windows you see and things are Java scripting, and they're all using this virtual machine that you installed. And now it's owned by Oracle because it was originally written for Sun, by Sun Microsystems. And then when they went out, the only thing Oracle really got from them was Java. They didn't keep any of the hardware stuff. They just kept the software stuff. And Java was one they wanted. So it works very well. The Java machine is similar to a virtual machine. I kind of don't think of it as a machine. I think of it more as a Windows service. It's a service that provides service, but they think of it as a machine because it all runs within this domain. What's nice about it, though, is it can run on different platforms. That was what makes it nice. I also teach Visual Basic. Before I meet you guys, I have my Visual Basic CIS31 class from 5 to 7. And Visual Studio does not run natively on a Linux or on a Mac. They're trying to get there, but they just haven't got there yet. But Java does. Java will run the same Java code you write on Windows will run in Linux or the Mac nicely. You might have to change some names or something, file names or things like that. But the basic code should run. Any questions on that? We're almost done. I've got like a minute left. I'm going to come back to the debugging with you guys next time. So we left off at slide 46. Slide 46. This is a big chapter. This is a lot of stuff. Okay, so I just want to make a note of that here. You finished. Okay. Started chapter 2, slide 46. Yes, Kang, you are exactly right. I will answer the next week's CC Confer question. I will answer that either next Tuesday or Thursday, so you'll have it in your notes in the session, so that you'll be able to answer that. The way I typically do it is I answer it online. I go to the grade sheet, and you guys answer it, and I can show you if you got it or not. Of course, if you're not online at that time, I can't say that. But that's what I typically do to make sure people get it correctly. But the answer will be in the session recording. Any other questions? Well, I want you guys to have a great weekend. I hope it wasn't too technical for you guys. I just wanted to illustrate the things that I was saying and what the author was trying to tell us. I'll repost this. And we have our we have the stuff on here. You know, it's the information that I provided here. All of this, well, wait, it's the wrong class. This stuff. That was my other class. So the resources are here of what I talked about, and the more that you read, the better off you'll understand. The more you read of this stuff, the better you'll understand it. Okay? The more you read, the better you'll understand it. This is a good video. Another student last year found this. So if you go through this video, it explains it pretty well. Okay. I'm going to stop desktop sharing. I want to say thank you all for participating. Use the discussion. I will check that out, see if there's any questions. You can always email me. And I want you to have a great weekend. And I want to thank each of you individually and personally for being here. And for the students that are reviewing this on the recording, just review it until it makes sense, or eliminate the hardware discussion. Don't worry about all those details. Okay? All right. Have a good one. I'm going to stop the recording.